To understand astronomy, we need to understand the terminology and some of the background ideas. And so chapters 1 and 2 largely involve a lot of these background ideas. So chapter 1, just basic terminology, basic ideas, basic sort of concepts. And then we get to chapter 2, and that talks about some of these ancient ideas of constellations and stars, and then some basic concepts such as the motions in the sky. And so that's kind of where we're going right now. We're talking about those kind of concepts, chapters 1 and chapters 2. So the stars and the planets are all extremely far away. The planets are millions of miles away from us, incredibly far. The stars are even farther. In fact, the fastest thing leaving our solar system is the Voyager 1 spacecraft launched in the mid-1970s. And it is on a path taking it out of the solar system, the fastest anything's ever gone. And even though it's not going towards the nearest star, if it were, it would still take 74,000 years just to reach that nearest star. And so that gives you an idea how big space is. In fact, it is so far away that light, which actually travels at 186,000 miles every second, takes years to get to us from stars. The closest star is about 4 1/3 light years away, and light years defined to be the distance that light travels in 1 year, and that's about 9.5 trillion kilometers, or about 6 trillion miles. The moon's pretty far itself. The moon's the closest thing to us, and so it's still over 250,000 miles away. You take a standard Boeing 737 aircraft at cruising speed, it would take 20 days straight at that speed, and that's reasonably fast, to get to the moon. Which gives you an idea just how fast the astronauts were going to get to the moon in the Apollo program, because it only took them 3 days to get there. So that tells you how fast that rocket was going that pushed them towards the moon. Planets even farther away. Planets are typically in the millions or tens of millions of miles away, or in many cases, hundreds of millions of miles away. I guess they're never even just millions of miles away. They are tens of millions to hundreds of millions to billions of miles away. So far away, we often refer to the distance in astronomical units. An astronomical unit is about 93 million miles. That's about 1.5 times 10 to the 8th, or that's 150 million kilometers. Well, what the heck is an astronomical unit? It's the average distance between the Earth and the Sun. So why would they pick such a weird unit? Well, it has to do with how we measure star distances. For how do you actually find distance? You want to measure the distance, so you're trying to buy a piece of furniture and you want it to fit in a spot in the house, so you use a yardstick or a tape measure or something like that to measure how big the opening is you want your furniture to fit in, or you want to measure, for example, the length of a street. An architect or an engineer is trying to measure a street. You surveying. To do surveying, what you basically do is you set up a spot and you take a reading as to what direction something is. Then you move to another known spot and take a reading to where something is, and you use trigonometry and geometry to triangulate on where things are and how far they are. So we do this to measure distances to stars. So to measure the distance to a star, because you can't just measure the distance. How do you measure, for example, how far it is from here to Houston? Well, you drive and look at the odometer. It's a lot tougher to measure the distance from here to Paris, France, because you can't. There are no odometers on ships or aircraft, and so you have to do a whole lot of what we call geodesy, or very complicated measurements and geometry of the Earth to figure out that distance. Okay, measuring distances to planets is even tougher. Spacecraft don't have odometers. How do you measure how far the moon is? How do you measure how far other planets are? And stars, if it takes tens of thousands of years to get to the nearest star, how do you measure that distance? And we triangulate on it. So as Earth goes around the sun, what happens is that Earth going around the sun here, Earth going around the sun has view of a star, and then it sees the star from a different angle, and you measure that angle. If you know how far it is across Earth's orbit, you can use geometry to figure out that distance right there. And so astronomers would define that distance. Well, here's the problem. They didn't really know how far Earth was from the sun at first. And so they were measuring that distance in terms of an unknown distance. In fact, Johannes Kepler was able to calculate that the relative spacing of the planets was based on how long it took around to go around the sun. And he says, well, if for example, Jupiter goes around the sun in 12 years, Earth goes around in 1 year, he has an equation, Kepler's law, which tells him that the distance is 5.2 times how far Earth is from the sun. Mars is about 1.4 times Earth's distance from the sun. Venus is about 0.7. Mercury about 0.4. Saturn is about 9.5 times farther from the sun than the Earth, except they didn't know how far Earth was from the sun. So they said, well, we know the relative spacing of all these things, so they just come up with a new unit that they call the astronomical unit. That's the distance Earth is from the sun, because that's what they knew everything relative to. And so we talk about Jupiter orbiting the sun at 5.2 AU. Saturn orbits the sun about 9.5 AU. Pluto's about 39 AU from the sun on average. And so this gives us the kind of way that we make these measurements. Okay, and so all these measurements based on a concept that we call parallax, and these parallax measurements, there's this apparent angle difference here that you see if Earth is in one